We now start a new chapter of the material that aims to understand what are some of the benefits and properties and even the pitfalls of using feedback control versus perhaps open loop control or some other mechanism. To do so, first I want you to consider the diagrams that I have on this first page here that indicate the two basic types or categories of control systems that we encounter. The first one is open loop control, and in open loop control we have the reference signal that we would like the output of the system to track. That's what the user supplies. Somehow that reference signal is manipulated by the controller to produce a control input to the plant, U of t, and that signal actuates the plant and produces an output Y of t. Something that makes life a little bit complicated is that there's always this disturbance that can influence the plant, and we've talked about all these things before. So the disturbance in a cruise control system might be the wind that buffets the car or some uneven road grade that influences the car's speed, but it's not something that we directly have control over, but we need to do something about. The closed loop control system, again, we've seen this before, but it's repeated here. Again, we do have the reference input to the system, but that reference input, instead of being fed directly to the controller, is compared against the actual output to see how well we're doing, and it's the difference between those two that is used as an input to the controller. The controller also produces a signal U of t that goes into the plant, and again there are still disturbances, but we now have a better mechanism to do something about it, as we'll find out, because the disturbances are part of what gets measured by the sensor. So those are the two basic categories, and there's variations of both of those, but that's the general idea. Again, our goal in this chapter is to compare these two, compare open loop and closed loop control. We want to show why the feedback or closed loop control might be better, but also why it is not necessarily better, and why we have to be careful when we're designing closed loop or feedback controllers in order to ensure that in fact it's a robust and stable and so forth system when we're done. We are, over the course of the next sections, going to evaluate these two categories of controller in a number of different ways. We're going to see how well the controller is able to remove disturbance or attenuate disturbance in the output of the plant. We're going to see how well the controller is able to deal with uncertainties and the plant parameter values. We're going to see how well the controller is able to cause the plant to dynamically track this reference input, R of t, and we're going to see how well it's able to eliminate steady-state differences between Y of t and R of t. We're thinking as time gets large, and we'll also think about stability. So a lot of different ways that we can evaluate controllers, and we'll look at those here before going on to subsequent chapters, which are going to be interested in more analysis and finally design of feedback controllers. In this chapter, we are going to use a really extended example. So this section that we're in right now has the goal of setting up the example that will be used. And we're going to be looking at speed control for a DC motor. You might recall that we developed the equations of motion for a DC motor back in Chapter 2. The picture is repeated here. The difference between this and what we did then is we have now added a load torque to the system, but to refresh your memory, to the DC motor, our input is an applied voltage. That voltage induces a current through the armature of the motor, and there's dynamics introduced in that because of the resistance of the armature coil and the inductance of the armature coil, and then the back EMF caused by this armature coil spinning. But as it spins, the output of the motor is going to be the position theta of t, and there's going to be a motor torque also that is able to accelerate a load with the moment of inertia J and some friction constant B. And that is a constant load. It's like a mass. It's a constant inertia anyway. But we have the possibility of a variable load tau L as a function of time that is also applied in the case we're looking at here. So tau L is a time-varying signal. We don't have any measurement of it directly, and we don't have any influence over it directly. So that will act as our disturbance input to this example. Recalling the equations that we developed before, they are duplicated here just for convenience. We had the two main equations. The first one was the mechanical equation that was Newton's second law applied to a rotating frame. So J times the second derivative of angular position plus B times the first derivative of angular position was equal to the motor torque constant times the armature current. And then also there's this load torque that's added to that. This is new. And then we also have the electrical equation, and that says that the applied voltage is equal to all the voltage drops. So EB, the back EMF, was an electrical constant KE times the velocity, rotational velocity of the shaft. And then the voltage drop over the inductor is LA dIA by dt, and the voltage drop over the resistor was just R times I. These were the equations that we developed with now the additional load torque, and that is where we left the equations when we finished Chapter 2. Now we've seen the Laplace transform in Chapter 3, and now we're prepared to manipulate these to find a transfer function of this system from the input EA of t to some desired output. And the desired output could be motor speed, could be motor position, but we're going to choose motor speed to be our desired output. And so we're saying let the output Y from our system, our value of interest, be theta dot. And again, the disturbance, W, is going to be equal to tau, this torque, load torque. So with those substitutions, the theta double dot, because Y equals theta dot, that becomes Y dot. The theta dot becomes Y, and the load torque is W. That's all we've changed in that first equation, and then the second equation is not actually changed at, oh yes it is, the theta dot becomes Y in that one place, otherwise there's no change. What we do with these is we are going to first take the Laplace transform of both equations term by term, and then that will change the differential equations into algebra equations, and we can then solve for Y in terms of EA, so the output in terms of the input, and the the disturbance also. So for the first equation, we take the Laplace transform of the first term, J times Y dot becomes S times J times Y of S. B times Y becomes B times Y of S. K tau IA of S, and W is W of S. In the second equation, KEY of S, L dIA by dt is S times L times IA of S. R times IA, R times IA, and EA is EA. So the only thing we had to remember to do that was the differentiation rule that said that a time derivative has a Laplace transform that multiplies the time derivative quantity by S. And when we're doing this, we're also assuming the initial conditions are 0 because we're aiming for a transfer function for the system, and the assumption when you're making a transfer function is always that the initial conditions are 0. So we've got two equations. The first one is what I call the mechanical equation. It has to do with the rotation of this inertia. The second one is the electrical equation. So let's work with the mechanical equation first. And what we're going to do is we're going to solve this for IA, or isolate, if you wish, IA of S in this equation. The first thing I did was simply to rewrite the equation so it's conveniently handy. And then I leave the IA term on one side, which is over here, and I move the W over to the other side. So this actually moves over there, and this becomes there, and it's minus because it was moved over to the other side of the equation. Then from this line to that line, I simply divided by k tau. Now I have an expression for IA as a function of S. And I guess I also combined a couple of like terms. This is S times J times Y, and this is B times Y, so I have factored out Sj plus B. We are now going to work with the electrical equation. So there is the electrical equation, and once again I have rewritten it. And what we will do is we will take the IA of S that we just found, and we will substitute that in to the electrical equation where it belongs. So in the first term here, Ke times Y, that is not changed, but then I've got S times L plus R, all times IA, so this is the equation we found for IA of S back there. Sj plus B times Y minus W over k tau, and then that all equals EA of S. Our goal here is to get an equation that expresses the output in terms of the input and the disturbance. So we would like to isolate Y in this equation. So we're going to do some algebra to get there. First thing, you'll notice that I've just rewritten that equation from the bottom of page 2 onto the top of page 3, so it's easier for us to work with it. And then we can combine some terms here. One thing is this k tau in the denominator makes it a little difficult to work with, so I multiplied both sides of the expression by k tau. So you'll see that the k tau is there. Where I had a key, I've now got a k tau, key. And then I had an SLA plus R, SLA plus R. And then JS plus B times Y, JS plus B times Y. And I also have this S times LA plus R minus W times minus W, which I've rewritten instead on this side as plus SLA plus R all times W. And again, the k tau multiplied this EA term. Now we notice on the left-hand side, all of these terms involve a Y of S. So I have multiplied out this term right here, and just using the FOIL rule. And so that's going to be S squared LAJ from this first here, multiplying that by that gives me that. And then I'm going to have SLA times B and Sj times Ra. And so those are here. Those are the terms multiplying S. And then I'm going to have Ra times B times Y, and also this K tau Ke times Y. So altogether we get that expression multiplying Y of S. On the right-hand side of the equation, nothing changed. We're going to clean up a little bit this by dividing both sides of the equation by this term, and that will leave a 1 in that position. And when we do that, this JLAS squared becomes JLAS squared divided by that term. The BLA plus JRAS becomes that term divided by this, and so forth. All the terms have been divided by that. When we see this, we see that the left-hand side is a second-order polynomial. So we know by the fundamental theorem of algebra that that can be factored into two parts, and we could even do the quadratic rule and find out exactly what those two parts are. But for here, I'm just going to simply say that I can factor it into some tau 1s plus 1 times tau 2s plus 1. I don't know exactly what that tau 1 and tau 2 are, and that doesn't actually matter too much for this example, but roughly it turns out that one of these time constants is dominated by the mechanical response of the system, and one of them is dominated by the electrical response. Generally, the electrical response is very fast, mechanical is very slow, so we can imagine that this is probably going to be one pole close to the origin, that's the slow one, and one pole farther away, that's the faster electrical one. Looking at the right-hand side of the equation, I've got the k tau over B times Ra plus k tau Ke all times Ea, and I've got a term multiplying W. Very often when we're working with these equations, people look at this and say, well, because I know the mechanical time constants of the system are so much faster, the mechanicals are so much slower than the electrical, we can often even remove the inductor completely from the circuit and not worry about that. We're not going to remove the inductor entirely from this, but we are going to look at this and say that term is probably negligible in this grand scheme of things. So if I make that assumption, then I've got a constant times Ea plus a constant times W, and we'll just name those constants A and B. And then A is written down here. That is not an approximation, but B is an approximation because that LA times S was removed. And what we've done is we've really removed a 0 here. If you think about it, the numerator polynomial in the process, which has made our dynamics a little bit simpler, but it's so fast that it's so far in the left half plane that it's probably a good thing to, it's an okay thing to do. So at the end of this example, what we have is we have this relationship. We have some time constant times S plus 1 times another time constant times S plus 1 all times the output equals A times the input voltage plus B times the input load torque disturbance. And I can divide both sides by the tau 1, tau 2 term, and I end up with this relationship here. So that was the goal of this section, was to set up this example, this DC motor example, for us to be able to look at it and compare the performance of different controllers applied to this system. If you want to write this in a block diagram form, it might be helpful for you to think about it that way. What we have is we have the actual input, EA of S, and that is going through going through this transfer function, well, I guess we could say that it's going through a gain A, and we have the disturbance input, which is not the desired input, but it's still there. That's going through B. Both of these are coming together, and both of them are going through 1 over the tau 1s plus 1, tau 2s plus 1 block, like that, and then producing y of s. There's different ways of writing it. We'll see another one soon, but that is generally what's happening in the system. So, with no further ado, we conclude this section and we'll move on to look at the first advantage of feedback.